that's where the mistake
So
is.
the number stays the same, but the unit changed.
Yeah.
Okay.
How about this one?
Volume. Well, in this case, you remember that equation there, we have, say, atomic average, weighted average atomic mass, and weighted average atomic mass equals to the percentage times the isotope mass 1 plus the percentage times isotope. Okay. So in this question there, we say bromine has 2 isotopes, and one of them is 79.934. The percentage. Probably. Oh, that's the homework. I thought it was the example that we run in. So calculate the amount of that. Okay. So this, in this case, we give you the average. So this number is given. So that's 79.904 equals to now 80.19163. 80.1963 times the percentage there. This percentage is 0.1931. Now plus x is the isotope that we're trying to determine. The percentage. What are you determining? How are you determining the percentage of this one? Well, you have 2 isotopes in there. Adds up to 100%. So if this one is 49.31%, the other would be 50.69% or 0.5069. 101 minus this number. Okay. So this number equals to this plus this. X is equal to. That's all for x when we get it.
One question, like, how did they answer, like, how come I got 50.96%?
Can't be there. Can't be that. It's this number times this number, that's roughly about 40 something. And 79 minus 40 something, that's 50 something, 50 something. Divided by 50 something. So that should give you somewhere around 79. So punch the number in calculator and double check it to get the calculation. So this is different from what we run as an example in class there. In class we ask you to figure out this number, giving you the percentage of each and the isotope, the mass of each isotope there. Now in this case we give you this number and one of the isotope is not different.
What kind of test it is?
No, yeah, no, it's a fair game. I would test you on these things there since it's one of the things that we talked about.
And last thing, I couldn't figure out why my percent error is large. This one and this one.
This number is not bad. Talk about it. It's not 3.98 times 10 to the second. It's 3.98 alone. So this number will change because this number is decreased by 100-fold. This number is 8 point six something. The true value is 8.3 something. The percent error shouldn't be very long. It should be relatively small. You gotta plug in the correct number here and here. Because if this number changes, this number will also change. And this number changes, this number will also change.
So this number would go in that it's.
No, this number won't go anywhere. It's mass over volume give you the density. So the density, calculation of density, you have the mass, you have the volume here.
Okay.
You gotta figure out the density first. And then when you calculate the percent error, then whatever density you figure out minus this divided by this, I won't give you the percent error. But right now, this number is off by 10-fold. So that's where the mistake comes. Now again, the things involved in the laboratory there, and it's mainly the thing that we do in the laboratory there is about dimensional analysis. Pretty much we ask you to measure a quantity, you identify the conversion factor and then do the calculations there. Okay? And there are separate things introduced in the laboratory, like the percent error calculation. Those are the equations you actually have to memorize, because those are, and when we talk about the percent error in laboratory there, and we say percent error is an evaluation of how accurate your result is. So when you're doing the calculation for the percent error, say we ask you to determine the density of a sample there, the smaller the percent error, the more accurate your measurement is. So that's what we're looking for. And when you end up with larger than accepted percent error, and then there's something wrong with either the measurement yourself, the measurement you did yourself, or it could be the something wrong with the measuring equipment there. Okay. Now, in the case of the density lab that we did on Thursday, we give you a solid cylinder. We ask you to determine the density by 2 different methods. Using a digital vernier caliper, you can read to the 2nd decimal place. Using a graduate cylinder, you can only get to the 1st decimal place. So that tells you the graduate cylinder for water displacement method, the volume you obtain from that method is not going to be as accurate as the volume you determine by measuring the dimension, diameter, radius, and the length. Okay? So you should expect a lower percent error when you use vernier caliper. And the water displacement method should give you a higher percent error. Now, what is an acceptable percent error range there? And normally at this level when we're doing measurements there, if you get anything less than 5% in terms of percent error, if you get less than 5% error, that's considered as a pretty good result. Anything between 5 to 10% would be acceptable. Beyond 10%, it's either you didn't do the measurement correctly, or the equipment that we're using is not accurate enough. So those are the things that we need you to think about when you do the laboratory activities there. And laboratory is the part, integral part of this course there. So you have to make sure that you always think about what we're talking about, what we are discussing in the lecture versus how do we use that information in actual measurement. And there's always an application part of the theory that we covered in the lecture there. Okay, so that's something that you do want to pay attention to. And when you are doing the measurements there, you have to pay very close attention to the accuracy of the equipment that we're using. We try to mention this in the laboratory there, and every time you measure a mass on an analytical balance, the mass you have to record 4 decimal places, okay, because the balance measures to the 4th decimal place. And if you're doing a vernier caliper, if you're using a vernier caliper to measure, you can read to the 2nd decimal place and you have to record everything. Okay? And otherwise, we wouldn't spend that kind of money to buy those equipment, expensive equipment. Like, I don't know if your Professor Brown ever told you there, because I'm always looking at, what we're using, why we're using it, why are we spending this kind of money. Those of you who are in my lab, when we were talking about the balance there, I told you those analytical balances cost about $3,000 when we buy those each, when we buy those analytical balances there. And the reason we spend that much money is because we need that kind of accuracy. The balances you see in the lab, outside of the balance room there, we only spend a couple $100 for those balances that measures to the 2nd and 3rd decimal place. And for